Hello everyone, welcome back to the latest lecture session. Again, a quick recap of what we have been up to. So in the context of remediating groundwater, we are talking about or discussing a relevant aspect, let's say, and that was permeable reactive barriers, right? And we discussed that in some detail. And today we are going to look into the design of the relevant PRB. Design in the sense that typically we need to be able to calculate the thickness of the PRB, right? So that's something we are going to look into. But obviously, before I go into that particular aspect, let's say the relevant aspects with respect to design, we need to also look at the applications of, let's say, how to apply this particular mass balance for a particular control volume. So some of you might have been or might be familiar with the relevant aspects of mass balance and applying them to different kinds of systems, but again we are going to spend maybe 15 to 20 minutes on this particular mass balance, because that is a key aspect in in this particular design and also maybe throughout other aspects in the course, right? So again, why do I need to look at this mass balance? So think of this now, you have the groundwater coming in this direction and I have my PRB here, right? And the groundwater flows through the PRB, the relevant reactions occur inside the PRB, let's say, right? And then you have the relatively treated groundwater leaving the system now, right? So now I want to be able to estimate or predict what happens inside this particular PRB, right? So only then can I decide what is the thickness of the PRB, right? Or let's say if I conduct some pilot scale study, let's say, right, to check for the relevant feasibility or such of the system, right? And I want to scale it up, again I need to be able to look at the relevant aspects with respect to scaling. Again I need to come back to mass balance, right? So in that context we are going to look at mass balance, right? So what is this mass balance about? Again, some people might have some background in this area, but again very much worth going over this again. Yes, so let's say I'm in a room and it's an entirely closed system, right? I mean, no windows, no doors, or the doors are locked and so on. So there is no flow of any fluid coming in or going out, right? And let's say if there is some particular contaminant that's released here, let's say a toxic compound that's released here, right? And let's say all the fans in this particular room are turned on, let's say, right? And then I want to be able to calculate, let's say, the relevant concentration or change in concentration of the relevant compound in this room with time, right? So that I can know when will I be affected, or because let's say I know the concentrations at which I will be affected, let's say, right? Or let's say if I know that, let's say for a compound X, if I am exposed to 10 ppm concentration for 10 minutes, I am going to have some adverse effects or response, let's say, right? And let's say in this context I want to be able to calculate when the concentrations will reach such a value, right? How do I do that? Again, I am going to consider this particular room as my control volume, right? Apply the relevant mass balance equation and then look at how the concentration changes with time, right? And then calculate the relevant aspects, right? So in this aspects, let's look at what we are up to. So typically when I look at or try to understand mass or material balance, let's say material balance, right? What am I looking at? I am looking at trying to understand how a particular compound's concentration or its mass, let's say, changes in a given control volume, let's say, right? So obviously what do I need to identify? I need to be able to identify the compound upon which I am applying the mass balance, obviously, right? So I am going to first identify the compound upon which I am applying the mass balance, and then I am going to identify the control volume. So obviously identifying the relevant compound is relatively simple, but identifying the relevant control volume, let's say, is sometimes tricky, and we are going to look at some of the minor aspects in that regard, I guess, right? So for example, let's say consider this to be a 3D box, let's say, hopefully, okay, I seem to have gotten the hang of this. Again, let's say some flow is coming in this direction X and again leaving here, right? And I have a relevant compound, let's say A, right? That's again coming in A naught or A in, let's call this A in, and A out, and the flow is Q, let's say, Q coming in, Q going out. And let's say now I want to be able to understand what's the concentration of the relevant compound A inside this particular control volume that we have here, right. So again we are going to try to apply this to microscopic scale systems, so that you can either apply it to microscopic scale systems itself, or try to understand that or extrapolate that to macroscopic systems, right. Again, so what is it that we have here? I want to understand what's happening to the relevant compound inside this particular control volume, and what's my compound? This is compound A. So what am I concerned with? So dm or mass, let's say, let me use the small m, dm by dt, what will it be equal to? It will be equal to, let's say, if you can understand it, mass coming in minus mass going out, right. So change in mass, or mass is nothing but concentration of the compound into volume, right. So if the volume is constant, this will be V dc by dt, but for now we are going to say that we are looking at change in mass of the relevant compound with respect to time, and obviously what is that going to be equal to in this particular system? So you have some mass going in and you have some mass going out, let's say, yes. So if there is a difference in either the flows or some such aspects, or relevant aspects, let's say, right, obviously you are going to have accumulation of what do we say, the relevant compound, or greater loss compared to what's coming in, right, or degradation, not degradation, let's say, the opposite of accumulation, if I can say so, yes. So in this context, obviously what do I need to know? I need to know the mass that's coming in, or the flux of the compound that's coming in, and again flux of the relevant compound that's leaving the system, right. So obviously in this case, keep in mind that we are only looking at x direction for a simple case, but for complex systems, let's say groundwater or such, you can have mass fluxes in x, y and z directions, right, but here obviously we are looking at only the x direction for now anyway, right. So other than that, let's say if I have any other reactions occurring within the particular system, here we only consider the flow coming in or flux of the relevant compound coming in and leaving the system, but let's say you can also have some other chemical process inside the control volume, let's say, that can either lead to formation of the compound or loss of the compound, right. So there, let's say, I thus need to look at any other sources or sinks, right, and if it's relevant to the relevant, if I need to apply that for the relevant reactions forming the compound or any reactions leading to loss of the compound, so I will have to say it's plus volume into rate of formation minus rate of loss. Again, the units should be such that it's mass of the relevant compound per time, right. So that's something that we need to look at, right. So again, these are the units more or less. So again, these units too should be per time, the way we write that here, right. So if I look at this for microscopic systems, it is going to be relatively tricky or slightly tricky. So let's try to understand this for a macroscopic system, I guess, right. And here, how can I transform that into, let's say, instead of mass, I am going to now say dCV by dt is equal to mass coming in. Mass coming in is nothing but the flow rate Qn times concentration coming in, right. What are the units of Q? Volume of the fluid per time. And what are the concentration units of this concentration? Mass of the relevant compound per volume, right. So what are the units? They are mass per time, right. Again, units here too are mass per time, right. So again, Q in Cn minus mass going out, similarly Q out, C out, plus volume into rate of formation minus rate of loss. Pardon me, I should have the volume term outside. So it's rate of formation of the compound minus rate of loss of the compound. Again, let's look at the units here. So here you have volume, right, and what are the units of rate? Let's say they are change in concentration with time. Typically, obviously, let's say if you are trying to come up with some particular equation or trying to check, let's say, if the relevant variables you wrote down make sense, right. One of the ways obviously is to look at the units. Obviously, all the units need to be the same, and in this case we are trying to look at mass per time units, right. So here, let's say, volume units, and rate of formation is nothing but dC by dt, right. Typically I am looking at how is the concentration changing with time, similarly rate of loss, right. And in this context, the units are going to be, for concentration it's mass per volume and per time, right. So again, you see the units are mass per time here. So for all the 4 sets of or 5 sets of variables, we see that the units are mass per time, in the way that we have written this equation, right. But one aspect, as I mentioned, is that we wrote down the equation for macroscopic systems. In that sense, what I typically mean is that the control volume that I have here, let's say, in that context, typically when can we apply this particular equation? When the concentration of the compound inside the relevant volume is same throughout the volume or the reactor, right. So, but obviously when you have microscopic systems, let's say, right, you have concentration changing with distance. Yes, let us try to understand what we have, as in what did we, let me write this equation again. So, assuming that the volume is constant, it is going to be V dC by dt is equal to Q in Cn minus Q out C out plus volume into rate of formation of the compound minus rate of loss of the compound, right. So, V is the volume of the system or the reactor, right, volume of reactor or system, and C is the concentration of compound inside the reactor, concentration of compound inside the, let us say I will write this as volume of reactor. So, concentration of compound inside the reactor, right. So, obviously now as you see here, the fundamental assumption maybe is that, not maybe, that's apparent, is that the concentration within the reactor is the same throughout the reactor, right. That is what you see here, it's the concentration is only changing with time, not with space here, right. So, that is one aspect, again we will come back to that later. So, Q in and Q out are the flow coming in and out, flows coming in and out of the relevant fluid, right. Cn is the concentration coming in of the relevant compound, right, coming in. C out is the one that is going out, concentration of the compound in the flow that is leaving the system. Volume here again is the volume of the reactor, rate of formation and rate of loss, right, rate of or rates of formation and loss of the compound, let us say, right. Again that is what we have. Again what do we have? We are looking at change in mass or the concentration with time, that is equal to the mass coming in, mass going out, and any mass that is being, or the material that is being either formed or lost due to the relevant reactions, right. So, that is the fundamental, not fundamental, let us say the mass balance equation you can use for or apply to macroscopic systems, right. But let us say in groundwater, what is the scenario though, right. So, let us look at this. So, this is my ground surface, and let us say this is my groundwater here or water table here, and let us say contaminant has been released and it reaches the groundwater, and the groundwater is flowing in this direction, and now due to this particular groundwater flow, I am going to have a net flow of fluid in one direction. So, let us say I am going to have the plume to be spreading, right. So, this is the side view, obviously side view, right. So, here when I look at my particular system, let us say if I am considering this particular case, as in let us say there is a well here that is drawing water out, okay. So, I am concerned with a particular control volume, let us say, right. So, here let us say, as you can see, the concentration changes from one point inside the relevant reactor to the other, right. Again if I take this to be the x direction, right, as you can see, due to the effects of advection and dispersion and any other rates of loss of the relevant compounds are such, as the compound moves in this direction, let us say the concentration of the relevant compound changes, right. The concentration is different from this point, let us say 0 to x, let us say, right. The concentration is changing like this, let us say, yes. So, in that case obviously I cannot apply this particular equation to my system, right. Again when is that the case? When let us say the concentration is changing inside your particular volume, let us say, right. So, obviously what do I need to look at? I need to look at a microscopic scale, let us say of the relevant control volume, in which I will consider that the volume is relatively, not relatively, the constant within the control volume, right, and then apply the mass balance, right. So, again in that context I want to be able to what do we say, communicate the fundamental mass balance equation here. I will just briefly touch upon that, right. Typically understanding the basics is always what do we say, good way to go about analyzing problems. Let us say some of you are trying to understand system in greater detail, let us say these aspects are going to be relevant, but I'll just spend a few minutes, not a lot of time in this regard. So what do we have? We have, let's say, change in mass with time is equal to the mass coming in per time and mass going out per time, right, plus or minus sources or sinks, which typically are the relevant reactions leading to formation or loss of the compound, right. So in this case, and if I can transform this and such with respect to flux, so I have used the term flux. Flux, what does that mean? Mass coming in or going out depending upon what you are looking at per area per time, let's say, right. So if I can transform this, it transforms into, let's say, right, it's going to transform into plus the del product of the flux, right, is equal to plus or minus sources and sinks. Okay. So again, this is the flux. Flux can be due to advection, flux can be due to diffusion or dispersion in this in the context of groundwater, right. So again, advection, what do I mean by advection? Let's say if there is a flow of net flow of fluid in one particular direction, let's say, and the contaminant is then transported by that fluid, I would call that particular kind of transport to be advection. So diffusion, let's say, is typically driven by the concentration gradient, and it is random, yes, and you have different kinds, as in molecular diffusion. Let's say, as in right now in this room, there are no fans turned on. And an example I typically look at or give out is, I have a scent bottle, I open that up, and it will take some time, or after some time it will certainly reach the person sitting at the back of the room, right, even when there are no fans turned on. Why is that? Again, there is a concentration gradient between this particular location and there, and over time, let's say, the system will want to move in such a direction such that the potential of the particular control volume, or let's say in this case the concentration of the particular compound and inside the entire room is the same, right. So, but if I turn on the fans, obviously the guy sitting at the back of the room will be able to sense the relevant compound faster, right. So, the first case, when there are no fans, it would the transport is going to be due to molecular diffusion, and when the fans are turned on, the conditions are turbulent, right. But again, keep in mind that there is no net flow of fluid in any particular direction, right. So, it is a turbulent case, and you are going to have turbulent diffusion, which is typically faster than molecular diffusion, right. So, that is something to keep in mind. So, advection, it is going to be given by the velocity of the fluid, U is the velocity of the fluid times the concentration, and diffusion is going to be minus the diffusion coefficient of the relevant compound in the relevant media. One refers to the compound in media. For example, let us say compound X will have different diffusion coefficient in air, and the same compound will have a particular diffusion coefficient in water, right. So, obviously diffusion coefficient is dependent upon both the compound and the media times the del product of concentration, let us say. Why minus? Because you know, the concentration or the diffusion drives the system such that concentration, what do we say, or the compound tries to move from a location of higher concentration to a lower concentration, right. Again, scent bottle, higher concentration to lower concentration. So, that is what we have. Again, I will not spend more time in this regard. So, the flux is due to both advection and diffusion, and I plug them in and so on and so forth, and also assuming that let us say, what is it now, that there is flow only in the x direction, let us say. And before I go further, del product vector to scalar converter, let us say, and that will give me an idea about dou by dou x, or how is the relevant variable changing with space, let us say, right. So, when I say the del product, I am referring to the change of, let us say, in this context, flux with respect to x, y and z directions, right. What is that again? So, I have this particular control volume, right. So, when I say the del product of flux, I am concerned with flux going out in x direction, flux coming in x direction, and again y direction, let us say, and then z directions, right. So, again I am unable to draw a pretty good picture. So, the del product will give me an idea about all the flux in the 3 dimensions, let us say, going out and coming in, right. So, that is what I am trying to look at here. So, again I just apply these aspects and assuming that the flow is only in x direction, so that y and z I am going to neglect them, right. So, it is going to transform as dc by dt plus, and also assuming that velocity is constant, velocity of that particular fluid is constant. So, I am going to have u del product of C is equal to, I am going to take the diffusion term onto the right hand side, is equal to the diffusion coefficient times, right, plus or minus sources or sinks, and in our case they are rates of formation and rates of loss, right. So, I will simplify this further according to what I have here, right. So, dC by dt plus what do I have here, u dC by dx, because I am saying that there is, or assuming that flow is only in x direction, similar to the groundwater flow or groundwater condition, and then the diffusion coefficient or the dispersion coefficient, let us say, right, again second derivative, let us say, right, plus rate of formation minus rate of loss, right. So, this is the equation that you can typically apply, let us say, for microscopic systems too. So, if you have a more complex system wherein, let us say, you also have flow along y and z directions, then obviously you need to take that into account. But typically in the systems that we are concerned with, typically we do not we as in environmental engineers, or most environmental engineers anyway, are concerned with, we typically have flow in only one direction. For example, let us say I have Haridwar upstream and Roorkee downstream, and there is a Ganga canal flowing through from Haridwar to Roorkee, right, and that is more or less, what does that relate to? You have fluid flow in one particular direction. So, the compound is typically transported by advection, and when you have advection, typically you can neglect diffusion, right. So, if I am trying to apply it to the compound being transported from Haridwar to Roorkee, how will this equation further transform into? So, dC by dt plus u dC by dx. I can neglect the diffusion term, because whenever I have what do we say, advection, typically diffusion is relatively negligible, right. But that will not be the case obviously in groundwater, because the velocity of the flow of that particular fluid is pretty less. But in surface waters, the velocity of flow of that, or velocity of that particular fluid is relatively high, right. Thus, you can neglect diffusion, but not in the case of groundwater though. But let us say the case of a compound, in Haridwar, and this is Roorkee, and I have the Ganga canal, a compound is released here and it travels till Roorkee, and any other reactions might occur in this particular canal. So, how do I model that? Obviously by this particular reaction. What are the key aspects in this particular non-reaction, equation? What are the key aspects in this equation? First, you see that we are assuming that the system is not at steady state, or that concentration changes with time, right. And the second variable or set of variables, what does this tell you? That C changes with x, as in the concentration of the compound changes as the compound traverses from Haridwar to Roorkee, right. So, keep in mind that the concentration is changing with distance, dC by dx, right. What does that tell you? That the system, not the system, the concentration of the compound is changing with distance, yes. And now let us move on to the relevant aspects, or let me write that mass balance down. So, dC by dt plus u dC by dx is equal to rate of formation of the compound minus rate of loss of the compound, right. So, again, what does this give me an idea about? How the concentration is changing with time inside my reactor, right. My reactor can be now Haridwar to Roorkee, the entire Ganga canal stretch, let us say, right. And here, as I mentioned, C is changing with x, as in if this is my graph and this is x, let us say, and this is concentration of the compound. So, C is changing with distance here, right. So, C is changing with distance here, that is what you see. Keep in mind that C is changing with distance and not with time, as some people can say. So, when I am talking about changing with time, what do I need to do? I need to sit only in Haridwar or at the same point in space, right, and then measure how is the concentration changing with time. Why I reiterate this is that some people think that if I travel from Haridwar to Roorkee, and then take the concentration of the relevant compound, and if it changes, people think that it changes with time, not really. So, when you are looking at change in time, you need to keep all the other variables constant, including space, right. So, here when you are traveling from Haridwar to Roorkee, you are measuring the change in concentration with distance, not with time, right. So, at steady state, how does this particular equation transform into? Steady state means there is no change in any variable with respect to time. So, this particular equation or this term will be equal to 0. So, I just have u dc by dx is equal to rate of formation minus rate of loss, right, or dc by d derivative of x by u is equal to rate of formation minus rate of loss, and that is dc by d theta equal to rate of formation minus rate of loss. And what is theta? Theta is nothing but x by u, right. U is constant, x is the distance that the relevant compound has traveled. What is theta? Obviously, it is the hydraulic retention time, right. So, what does that give an idea about? It gives an idea about the average time, let us say the relevant compound or the the water molecule, or in this case compound, stays in that particular system, right, hydraulic retention time. How much time does the relevant compound stay in that particular system, right. So, here dc by d theta equal to rate of formation minus rate of loss. Obviously, this is at steady state, right. So, why is this particular aspect important? Let us try to understand our PRB here, right. This is the side view, this is the side view, okay, as in this is my PRB, the thickness of the PRB, let us say, and I have groundwater coming in, let us say, right, and then leaving the system too, right. And now I need to model what is happening or try to predict what is the behavior of the relevant compound inside this particular PRB, right. So, obviously, what kind of a system will that be similar to now, right, as in most people are familiar with three kinds of systems. One is batch, the other is CSTR or completely stirred tank reactor, or completely mixed flow reactor, or plug flow reactor, right. Plug flow as in flow through a particular, similar to flow through a particular pipe, or flow through a particular canal or such, right. So, batch reactor, what does that mean? I have a system and I have no flow coming in, no flow going out, but it is continuously stirred. I am using this symbol to say that the system is continuously stirred. So, the concentration of the relevant compound inside the reactor is the same. CSTR, what does that mean, or what does that refer to? You have flow coming in, you have flow going out, right, and it is again continuously stirred, right. So, it is a open system, but again the aspect is that the compound concentration within the reactor is the same. And plug flow reactor, so similar to what we just discussed, we can just let us apply it to the Ganga canal case. So, at Haridwar, flow coming in, and again I am looking at the case in Roorkee, flow going out, and the concentration here changes with distance here, right, concentration changes with distance here, right. So, again keep in mind that the concentration of the relevant compound is not same throughout the reactor, but is changing with distance here. So, we come across batch, CSTR and plug flow. So, batch reactors typical applications, let us say we looked at this room or any experiments you conduct in the lab, and CSTR or completely mixed flow reactor, any typical unit process in water or wastewater treatment, or most of them. So, you have activated sludge process, you have continuous mixing, you typically assume that the concentration of the relevant compound in your particular reactor is the same, right, or typically some lakes, let us say you can assume lakes to be behaving as a completely stirred tank reactor. Obviously, there will be deviations because in the actual case the concentration of the relevant compound throughout the reactor will not be the same in the case of lake. And then you can model the river or lake, not lake, pardon me, river or the stream or canal with a plug flow reactor, right. So, which of these three cases would apply to your PRB, right? I mean, we are discussing material balance and mass balance, yes, but obviously we need to be able to apply it to the PRB here, right. So, if you think of it, what is happening inside the PRB? You have, let us say, mass of the, not mass, pardon me, the zero valent iron or the reactive media in this particular thickness, let us say, right, and the compound is now reaching the relevant reactor and it comes in contact with the zero valent iron and the relevant reactions start. So, as it goes forth, it is still in contact, what happens? More reactions or rates of formation, let us say, or pardon me, rate of loss. And so, you are going to observe a decrease in the relevant compound concentration as you go from the face of the reactor to the back of the reactor being the PRB here, right. So, in this case, as you see, the concentration is changing with distance, right, and we are assuming that it is going to be uniform flow, one of the fundamental aspects for plug flow reactor, right. So, as you see here, your PRB can be modeled by the plug flow reactor, right, plug flow reactor, right. Now, let us try to apply that here. So, I have my PRB here and groundwater is coming in and going out, right. And what is happening inside this? If this is concentration and this is thickness of the PRB, and at steady state anyway, that is what we are typically discussing. So, if this is the case, how is it changing? The concentration is coming in at particular value C naught, let us say, and then decreasing, right, and then staying the same, right. So, this is obviously with distance. So, now I am going to use the relevant aspect derived with respect to the plug flow reactor aspect as in the material balance equation, dC by d theta equal to rate of formation minus rate of loss, right. So, that is the relevant application. So, obviously, how do I get to this stage? As you remember, I need to be able to understand the rate of loss, right. Typically, in our case for PRB, it is going to be dC by d theta is equal to the minus the rate of loss, right, rate of loss. The compound typically is not formed, the compound of concern anyway. So, if let us say I have A plus B goes to products, right, and we mentioned that let us say this is 0 valent iron and this is my contaminant. So, what is rate of loss in this case though, right? It is going to be the rate constant times concentration of A times concentration of B, right. It is a second order reaction, but as we discussed, what do we have? We have the surface area per volume of water, right, because it is 0 valent iron, you have pellets, right, and the water comes in, water or the compound comes in contact with these pellets. So, we are concerned about surface area per volume into the concentration of the relevant compound, let us say concentration of B here, right. And what is this depend upon? Again, as we know, the rate constant times A is depend upon the specific surface area and concentration of 0 valent iron into the concentration of the relevant contaminant or the compound, right. So, this is my rate of loss. So, obviously, I need to be able to calculate K, right. There are different compounds, right, and different kinds of 0 valent iron, or let us say different kinds of reactive media. How do I calculate K? So, initially I am going to conduct a experimental study in a batch reactor, right. So, batch reactor, yes, and what am I going to measure in this batch reactor? I am going to put in the relevant reactive media, let us say, and also the compound, right, and then I am going to measure the change in concentration with time, right. I am going to, this is my, these are my sample concentrations, let us say, and then I can fit a model. And what model will that be? Again, I need to apply the mass balance to this batch reactor. So, what was the mass balance for the macroscopic scale? It was V dC by dt, right, is equal to Qn Cn minus Q out C out plus volume into rate of formation minus rate of loss, right. Obviously, no flow coming in or flow going out, right, and let us say now I am concerned with or left with dC by dt is equal to rate of formation minus rate of loss. The compound is not being formed in this case, so this transforms into dC by dt equal to minus rate of loss, right. So, I have this particular case, and you know that you have the values with respect to concentration and time, that is what you measured, right, and now you can get the rates, and from that you can calculate the rate constant, right. So, once I calculate this rate constant, I can use that in my plug flow reactor relevant system and then apply that and get that through, right. So, looks like I am running out of time. So, I will apply this particular aspect in the next session, maybe 5 or 10 minutes, and then we will move on to the relevant case study that we discussed earlier, right. And I guess that is it from me for today, and thank you.